Hello, my name is Daniel Twitchen, and today I'm going to talk about the diamond quantum revolution. Or more specifically, really look at three things in this talk. The first is talk a little bit about why inherently diamond is a great cubic host material, to explain a little bit how we grow it, and then if you can control its properties, the quantum properties can be quite unique and quite special. Then the second, talk a little bit about some of those quantum spins we can engineer into the material and application of that, particularly focusing on magnetic field sensing. And then the last part of the talk will just reveal some news, which we're very excited about, launching a new quantum grade of diamond. So many of you will be aware of some of diamond's engineering appeal. For example, its hardness, its optical properties, and the visible that the gem guys will tell you about. But perhaps less of you will be aware, for example, this wafer I have in front of me has a thermal conductivity in excess of 2,000 watts per meter per K, more than 5 times higher than copper, more than 10 times higher than your typical ceramic conductor. Now that thermal conductivity stems from its material properties, and if you're interested in high power electronics, where in telecoms or maybe in radar, where you're trying to dissipate heat, mounting those electronics on diamond gives you a way of really driving performance and keeping those electronics cool to also give reliability. So these multifunctional properties of diamond have been known for a while, some more common than others, but really the key is how do we access them? How do we grow diamond, and how do we tailor the properties to suit the different applications that those properties might enable? And it's really been chemical vapor deposition that sort of unleashed its potential. So the last 10 or 15 years, there's been a great deal of progress in growing diamond using CVD techniques. So the schematic on the left shows a typical microwave chamber. So we're coupling energy, typically in the form of microwaves, into a resonant chamber. Into that resonant chamber, we're feeding gases, methane and hydrogen. Methane is obviously the source of carbon, but if you like, the magic comes from the hydrogen. So by heating those gases up with that microwave energy to about 3,000 Kelvin, we end up producing a plasma, a super species of carbon and hydrogen species. The substrate, the thing you can just see in red below the bright plasma, is typically much cooler, around 1,000 Kelvin. So the carbon atoms precipitate out onto that substrate, both as sp2, graphitic phases, and also as sp3, diamond phases of carbon. That, if you like, is where the magic from the hydrogen comes in, because we've dissociated the molecular hydrogen into atomic hydrogen. Atomic hydrogen is much more effective at etching away graphite, sp2, than it is diamond. So by having a high fraction of atomic hydrogen, we can actually end up growing diamond, if you like, by default, under conditions you would not normally expect diamond to be thermodynamically stable. It's fair to say for us as material scientists, the requirements of making quantum diamond, if you like, the highest purity diamond, has really put a huge amount of pressure on us understanding all the interlinked factors, from the power coupling, the gas phase thermodynamics, the surface kinetics, fluxes and surface factors like surface temperature, and even bulk factors like the surface finish, the orientation of the surface, the dislocation content of the diamond we're growing. All of those things need to be considered and put together, and that's really what my colleagues and I have worked on pretty much over the last 10 years to develop quantum grade diamond. And in the notes to the talk, you'll see a link to a video where you can actually watch diamond grow. So that's how, in simple terms, how we grow high quality diamond. Why might it be expected to be a good host for qubits? Well, you think about a quantum spin. So if this is my qubit, you see there my little north-south magnet at the top of the image. Typically, you want to minimize its dephasing. You don't want this thing to dephase because of interaction with other spins or phonons in the crystal. Typically, those dephasing characteristics are characterized by characteristic times, T1 and T2. So T2 is the measure of spin-spin interaction. So in an ideal world, you'd have a perfect lattice with your quantum spin and no other spins in the environment. Other spins might include, for example, the nuclear spins associated with the host lattice. So ideally, you want a host lattice which has no nuclear spins in. diamond comes pretty close to hitting that milestone. 99% of all carbon atoms are carbon-12 and that have a nuclear spin 0, and only 1% have a nuclear spin half. The second is interaction with phonons. So in the same way, diamond is a very good conductor of heat, which I talked briefly about at the beginning. Light atoms, short, stiff bonds, which means vibrations move through the crystal lattice very fast, means actually the spin lattice relaxation time is very long. Actually, those phonons interact very weakly with electronic spins. So as a consequence of that, your quantum spin is pretty isolated from the environment. And that means, in principle, you might expect very desirable properties, even at room temperature, without having to freeze out those dephasing mechanisms like many other competing materials have to do. The high symmetry of the diamond lattice, all atoms equivalent, nice cubic lattice, means you've got consistent reproducible behavior. So if that's why diamond is inherently a good host, at the end of the day, you need a quantum spin. You need something to act on and measure. There have been many defect centers in diamond explored, things like the silicon vacancy, germanium vacancy, but by far the most common explored is what's referred to as the nitrogen vacancy defect in diamond. The image on the left illustrates its structure. It really is a carbon atom substituted for a nitrogen atom, and one of the nearby carbon atoms substituted with a gap, a vacancy, a hole. That nitrogen vacancy center in the negative charge state has a spin, an electronic spin, so that's your quantum spin. Once formed, it's stable to temperatures in excess of 1800 degrees centigrade, so it's a very stable defect center. So that's your quantum spin. The next thing you'd like to be able to do is manipulate it in some way. And this is, if you like, the magic of NV. It has a very unique set of energy levels. So in the ground state, it's a triplet state, but in the absence of a magnetic field, you can consider that basically as a 0 and a 1 state. You come along with a green photon or a photon with energy greater than the green part, about 550 nanometers. You can excite from the ground to the excited state. Now, the 0 goes up to 0 and relaxes back down, the 1 goes up to the 1 and relaxes down, but some of the electrons relaxing from that excited 1 state relax via those singlet states. What that means is that some of those 1 state electrons end back in the ground state. So actually, by exciting with green light, you can spin polarize this ground state to have more electrons in the 0 state than you'd expect from a Boltzmann distribution. In essence, a spin temperature of 0 Kelvin, or the bulk temperature might still be room temperature. So you can optically spin polarize. So now I have ability of manipulating that quantum state. What about readout? Well, I come along again with my green photon. I hit that NV defect. And guess what? Because I've got more electrons in my 0 state, the emitted light, which is in the red, about 637 nanometers, is brighter than the electrons excited from the 1 state. And you can see that on that image on the right-hand side of that little bright red. That really is emission coming from a diamond containing NV centers, and it's brighter. That's because electrons are coming from the 0 state, and slightly darker, and that's from the 1 state. So now you have the ability to optically read out. What about manipulate those states? Well, actually, quite conveniently, the gap between the 0 and the 1 state is around 3 gigahertz. So you can bring along a fairly conventional microwave source and drive transitions between the 0 and 1 ground states. And in that way, produce a superposition. Now, the final plot on the right-hand side is that measured intensity is a function of magnetic field as you sweep the microwave frequency. So there you see the dip. And that dip comes from electrons excited from the 1 state, so it's a bit darker. Now, if you apply a magnetic field, and you see the magnetic field increasing on the y-axis, you see that dip splitting. And that splitting is a direct consequence of the Zeeman interaction. So by measuring that splitting, by knowing a few fundamental constants, it's possible to directly measure the magnetic field. As far as we know, there's still no other system in material science that shows all these desirable characteristics, not least at room temperature. So I apologize that the writing here is quite small, but this slide here is really to get across what this has meant in terms of potential applications. So the combination of high purity material becoming available, the combination of actually the engineering being relatively simple. You need a green light source, you need an RF source, you need a photodetector. You don't need a dilution refrigerator. You don't need cryogens. And already you can start to manipulate quantum spins. And third, that really spectacular work from some leading academics around the world that allows an understanding of the physics in these processes, names like Arachuk, Yaletzko, Wadsworth, Lukin, key names that contribute an awful lot to this field and their collaborators. And there's been tremendous progress in the last 10 years where this centers on the basis of new opportunities and technologies as diverse as timing and gyroscopes to magnetic sensing. I don't have time to talk about too much today, but just to pull out, even in quantum networks, the work led by Professor Hansen's group in Delft, where they showed that they could entangle photons from two separate diamonds more than a kilometer apart, firstly to first loophole-free test of Bell's inequality, but importantly showing the building blocks of what a quantum repeater network might be using diamond. We've got these distributed entangled nodes. Really beautiful work published a couple of years ago. But the one I'm now going to spend the rest of the time on is really about bulk magnetic sensing. In many ways, that's the most mature of the technologies at this point in time, where you're using these NV centers to measure magnetic field. So I apologize, there's not been too many equations this week, but this equation has really led a lot of the material science. And in its simple form, it's relatively simple to explain. The first term, I should say, a magnetic field sensor, a key property is sensitivity. You want it to be sensitive. So how do you make a sensitive diamond magnetometer? What are the material parameters that affect that? So the first term you see is fundamental constants. The second term, that 1 over gamma square root of mu, that term really is a measure of the effectiveness of the red photons that you collect. So the red photons, which tell you about the state of that NV defect, you want to measure all of them. Every one you miss effectively is lost signal. So you'd like your detector to be collecting everything. There's also a term in that which actually says you want to measure the photons that come from the defect you care about and not other defects. So if you're getting other defects in the material emitting around the same part of the optical spectrum, then again, that's lost signal. But really, it's that last term, the 1 over square root of the number of NV centers multiplied by the characteristic dephasing time T2 star has been the parameters that have really driven the material science. So the plot on the right shows on the x-axis increasing number of spins. The y-axis is T2 star. So in simple terms, for a very low number of spins, the T2 star is a maximum because the spin in the material does not feel the impact of any other spins in the environment. As the number of nitrogen atoms increase, which have spin, all of a sudden your quantum spin, the spin you care about, starts to not only be influenced by the external field that you aren't trying to sense, but actually the background spins in the material. So that now begins to dominate the T2 star. So really you're trying to determine what's the optimum, the product of the number of spins multiplied by T2 star. And another parameter is things like the isotopic enrichment. So you see the blue curve there, and you see for a given nitrogen concentration, that's much higher than the red dash curve. And that's because that's in a diamond which is isotopically enriched. So even though I said there's only 1% of the carbon atoms that have nuclear spin, reducing that further does actually increase the T2 star, which means a better sensor. But that improvement runs out as the nitrogen concentration increases, because after a certain point, that background N starts to dominate over any benefits you might have from the carbon-12 enrichment. If only it was that easy. That plot naively would say the best sensor is a large block of diamond with a distributed concentration of NVs separated by a long distance. So large, meaning you still have a lot of NVs. The NVs separated, meaning that they don't feel the impact of each other. But in practice, when you start to build the engineering factors in, the ability to excite these, so how much green light you need to make sure you can excite the whole volume of the diamond. The practicalities of the RF field you apply to drive some of the transitions being uniform, because if it's not uniform, you lead again to a broadening of that optically detected magnetic resonance and reduced sensitivity, really sets an additional criteria. And it's something not that well explored in the literature, but really it's the combination of the material science and those engineering factors that allow you to tailor and optimize really the ultimate diamond you need for a specific application. And that's quite an important point. So to finish, so I introduced some of those terms that we care about, number of NV centers. So what does that mean for us from material science? Well, it's really important that as the science has progressed, the material understanding has progressed, and importantly, as part of that, the reproducibility of the material science. So here you see a batch of samples on the x-axis across a single run and across multiple runs, and on the y-axis, the concentration of nitrogen. There, within the measurement error, you can see the nitrogen concentration is consistent. So very good control of the nitrogen. That's really come from some of those gas phase and surface understandings of the synthesis process, which I talked about near the beginning. But it's not nitrogen we want, it's nitrogen vacancies that defects that have these desirable quantum properties. So we've got to turn it into NV. We've got to turn the N into NV. And to do that, we need to create vacancies in the material. Typically, you use high-energy electrons to irradiate the volume of the material, which knocks out carbon atoms and creates these vacancies, these gaps. Now, that plot on the left-hand bottom left shows the number of vacancies as characterized by the absorption feature of GR1, which is directly linked to vacancy concentration versus a radiation dose. And crudely, the vacancy concentrations are linked to the color of that blue color. So as you go across, you see it gets more intense, and that means we've got more vacancies. So by doing those sort of calibration curves, you know a certain dose produces a certain volume of vacancies. And what's been particularly important for us is showing the repeatability of this between runs. So doing the same dose today as we did last month and the month before, and that plot on the right shows repeatability of a desired vacancy production over a 12-month period. And again, within the error bars of our techniques to measure these things, very consistent. So that's how we make our vacancies. At the end of the day, we need to make nitrogen vacancies. Now, in the literature, it's well documented that vacancies in diamond become mobile, these gaps, around 700 degrees centigrade. So if you now take this diamond which has nitrogen and vacancies, the temperatures around 700 or above, the vacancies become mobile. The strain field around the nitrogen means that the nitrogen preferentially captures the vacancy. And once formed, that nitrogen vacancy center, as I said earlier, is a very stable defect. So here, if you like, in some ways, is one of the money slides where now you've got the number of samples of, again, within a run and across runs along the x-axis. And on the y-axis, the nitrogen vacancy concentrations. Again, with the measurement error of less than 4%, showing very good consistency. And there's some images and some samples at the bottom with this nitrogen vacancy concentration, which it goes from light pink to purple color, depending on the concentration. So if we now think briefly commercially, you think about the value chain. We as a material company are far on the left-hand side developing novel materials. Typically, when you've got a disruptive new material, it's the system guy that gets all the benefit. And really it's working with the system guy to get that benefit that leads to the pull through the chain. So in the last few years, we've worked on a number of customized applications with system integrators trying to come up with the right solution for their problem. And outside of that area, we were still offering diamond, but not necessarily treated diamond. So what combination of this work I reported earlier meant earlier this week, on the 15th of June, we actually launched our first generic general purpose grade of quantum diamond. We refer to it as the first of the DNV series, diamond nitrogen vacancy. B1, B standing for bulk. This is a uniform concentration of NVs through the volume of the material, 1 being linked to the nitrogen concentration in the material. And this material, we believe, is the first widely available material where there's guaranteed commitment in things like the number of NV defects and critical parameters like T2 star. So we're very excited by this, and we hope this really will help a whole new community come into this field and pick up the diamond and start working with it from day one and doing the clever things that might lead to. I do like the tagline, I will read it out: perfectly imperfect diamonds, uniquely designed for quantum applications. So I hope in today's talk I've managed to convince you that diamond is a powerful and unique cubic host material. And by getting on top of the control of the synthesis, it's now been possible to actually show very long decoherence times of the material, room temperature operation, and of course these unique characteristics to be able to optically initialize and read out all at room temperature. Magnetic field sensing, which is probably one of the more mature areas of this science and technology, is increasingly requiring a baseline, robust baseline of material. And that's what we've worked very hard to do in the last few years. And one of the outcomes of that has been the launch of DMD B1. So I'd like to thank you for listening, and I'd encourage any of you to send your questions or comments. We value feedback and insight to how we can help the community more. I should thank my colleagues who are shown in the inset. Great thanks to our partners here and our collaborators, particular collaborators note it's contributed almost since the beginning, guys in Harvard, Stuttgart, Warwick, and Delft, and thankful for all the funding support that this technology has received over the last 10 years, both in Europe and in the US. So thank you very much for listening.